Right, sorry about this. So thank you very much for your invitation, Samir and Sujay, to this apparently beautiful place. I haven't seen much of it except for the campus, but the campus is certainly very peaceful. So, right. So this is a follow-up on Kathrine's talk. I mean, in a slightly different tone. And you will see that some of my transparencies are a little bit an echo to some of the things that she already announced, so that will make my life a little bit easier. And you will also, especially in the first few transparencies, see again the elliptic genus, but it's because this is, in a way, a conference on mock modular forms, and I wanted to introduce my talk with the numbers in the elliptic genus that you know by heart by now, okay? But just emphasizing once more the fact that the mock modularity that enters into the elliptic genus can be traced back to the very early days of n equals 4 characters when I was calculating them with Toru Eguchi. So the plan of the talk is as follows. So, talking very briefly about the elliptic genus once more, showing you a slide with what the symmetry landscape is in non-linear K3 sigma models, and then going on to the meat of the talk, which is about our idea of combining symmetries of non-linear sigma models and reaching a new world, really, where we obtain the group that she mentioned before, Z2 to the 4 times A8, which is a maximal subgroup of M24, but crucially, as we said, not a subgroup of M23, and crucially as well, not a symmetry of any non-linear K3 sigma model. Right? So there is a jump there, conceptual one if you want, and I try to motivate why this conceptual jump is rooted in some things that we can check and prove. And then after talking about this from the geometric point of view, I will concentrate on a very specific type of conformal field theories, which are the Z2 or before of toroidal theories on K3, and look at a particular sector of the elliptic genus, namely the states in the massive sector which contribute to the leading order. So the coefficient multiplying the power q and the mock modular function, and that coefficient is 45 plus 45 complex conjugates, so 90. So here we go again. So this was basically a very DIY transparency to try to reflect once more on the fact that the elliptic genus, as we saw from Kathrine's talk, is an object that has been computed from completely purely geometric ideas, and of course there is an intertwining with our understanding of it from the conformal field theory, but really, Kathrine says this beautifully. I mean, we need the two approaches, hopefully, to make progress on moonshine. Now that the K3 elliptic genus is a weak Jacobi form of weight k equals 0 and index m equals 1, I'm sure you are quite saturated with this statement. So what is crucial in the moonshine is the fact that we have the notion of supersymmetry. Supersymmetry, as I will repeat in my next transparency, is basically at the heart of why you get modularity in the characters. And then, of course, the idea that you have strings to play with, that's another crucial ingredient in the game. So, what I'm aiming at recalculating here for you is the elliptic genus that you saw on the previous page, but using the n equals 4 characters, and in particular, the massless character in the Ramon sector here, for the what I call isospin 0. So I apologize, but my notations are different from Kathrine, that I put 0 here, and then I spectral flow to the Neveu-Schwarz sector. This gives me the massless matter sector, not the vacuum. So the 0 here doesn't mean vacuum in the Neveu-Schwarz sector, while in her case, she used a different convention. So these characters, and several people have already reintroduced these early in the week, Samir being one of them, where we have this blue mu function here, which depends on tau and z in the usual notations for tau and z. So z complex variable, tau complex variable in the upper half plane. And the famous upper-Lurch sum here. And basically the fact that we have a denominator here can be traced back to the fact that we have fermions and bosons, of course, but certainly fermions in the n equals 4 superconformal algebra, but we have singular vectors. And we have to take into account this BPS condition, and this means that you have to subtract from whatever partition function you would write generically for the fermions, you have to subtract some of them, right? So, and this denominator is very much linked to the fact that the modular transformation of the characters are in a way beautiful, but we didn't used to think that all these years back. We thought it was a complete nuisance that we couldn't really write beautiful formulas like everybody else was doing with the minimal models. You have to remember that at the time, n equals 1 and n equals 2 rational models were really the fashion. And of course, everybody was looking at this as being a mathematical curiosity and not an easy one to deal with. And indeed, in calculating the modular transformations of this upper-Lurch sum, we see that we get back, because there's a weight 1/2 here, but we get back the function itself and then a corrective term here, which happens to be the so-called Mordell integral. So if we reinsert this modular transformation in the character here, you see that actually it will go, the character will transform into itself up to a sign, and then an integral, so an infinite sum of massless character. And the fact that you have this continuum here of alphas here is a signature of the fact that you have a continuum of massive characters as well in the modular transformations. Now it turns out, and this is a result by Mordell quite a long time before us, that you can rewrite the Mordell integral, which is essentially modular invariant. Okay, there is a one Dedekind function in front here, and he has himself rewritten this Mordell integral in terms of a function h3, and of course expressing here that it's invariant in the S, or again as a combination of two other functions, h2 and h4 here at tau n minus 1 over tau. So this is due to Mordell. And it turns out that these three functions, h2, h4, and h3, are actually specialization of the upper-Lurch sum, which is here, okay, at three values of the variable z, which are at the torsion points, 1/2, tau plus 1 over 2, and tau over 2. And using this information, one can rewrite the massless character for isospin 0 here, so this one here, in three different equivalent ways. And these three ways have similarities. They all have one of these h functions multiplying a ratio here, theta 1 square over eta square, which is very closely related to the massive character at threshold. I mean, we're just missing a power of eta here, which we can easily fix. And then on the right-hand side, we see that these are really nice combinations, and these are exactly the combinations, the terms that appear in the elliptic genus that I showed you in the first place. So from here, multiplying by 8 each of these expressions here, we reproduce on the right-hand side the elliptic genus, and on the left-hand side we have the 24 contribution of this massless character at isospin 0, and then we have 8 times the sum of H2, H3, and H4 times this ratio there. And therefore, this is yet another way to encode the information about the moonshine here, because this sum of specialized upper Lurch sums here is actually the Mach modular form that you also have seen many times this week. So what I'm saying is that this is again possible because of the very nature of the conformal field theory that we are looking at. So it's intrinsically linked to this fermionic character and supersymmetric character of the theory. Right, and this was to introduce the the Mathieu moonshine, just in case nobody else would have talked about it before. Right. So, we all agree that the Mathieu moonshine is nested in the nonlinear sigma model, which describes a superstring, but actually it's something that happens at the level of the elliptic genus, and that was emphasized before as well this week, and probably, well, surely this is one of the reasons why we have so much difficulty to pin down how this M24 symmetry may act, because we are so used to looking at symmetries of field theories where all the states of the theory take part into the story, while here we restrict ourselves to a very specific set of BPS states, and not only that, but we have extremely subtle cancellations between fermions and bosons. So it's a really new arena, and when we compare with the monster moonshine, there are similarities, but there are also extremely deep differences, at least as I understand it at present. Crucially for us is the fact that this elliptic genus is an invariant on the moduli space. So it captures a symmetry, okay, which pertains to all nonlinear sigma models on K3, and therefore this was really something that Catherine and I were fascinated by. I mean, this idea, and all what we did about the surfing and the twist, but definitely the surfing, was actually trying to understand how we could imagine a symmetry that would be ambient on the moduli space, but yet not being a symmetry of any model here. We also expect a representation of M24 on the vector spaces of states that govern the elliptic genus, and our efforts were also guided by this expectation. So intrinsically what we do comes from the geometric approach, and Catherine already justified for you why we restricted to geometric symmetries. I'll just summarize this in a minute. And the second part about twisting here, I mean, there are lots of twists in conformal field theory. This is yet another one here. You will see at the very end of my talk what I mean by this. But by looking at the conformal field theory approach, we can gather evidence that our ideas coming from the more geometric thinking is actually quite sound. So it doesn't prove, we don't have an action of M24, of course, but right. So this was a one-slide summary of the symmetry landscape for all these nonlinear sigma models on K3. So let me get you through this. So Mukai and Kondo, as everybody has heard, had a classification of symplectic automorphisms of K3 surfaces, and they produce a classification that I will flick at you in a minute, and all the groups that they list are subgroups of M23, and I believe that this knowledge was the one that drove Eguchi to really look a little bit more closely at the atlas with respect to M23 first and also M24, so the two there. And that's how they got to their observation, is by just looking into the atlas while they were in Aspen one summer. So this obviously is an important result. And what we did is that we looked at a particular subclass of K3 surfaces where the geometry is encoded in a beautiful way, which serves our purpose, because there are lattices at play there that really help in our approach. But we see that there is another piece of impressive work here in red by Roberto and collaborators, Matthias, Stefan here as well. So where they studied symmetries that were beyond the geometric ones, so adding stringy symmetries with some restrictions, of course, because they wanted to preserve the n=4 superconformal algebra because of the structure of the elliptic genus. And as Katrina already mentioned, I mean, the surprising thing when the paper came out is that actually there are symmetries, there are models here which have symmetries that are not in M24. Of course, there is a more global group there, which is Conway 01 there. I've just put a little dot here just for advertisement, really. I'm not going to talk about that here, but Roberto here was instrumental into driving the calculation for a model which exhibits quite a large symmetry, Z2 to the 8 times M20. It's a beautiful set of calculations there, but this is again is in this region there. And then finally, just to set where we are here, we have this dashed line here, because these are not, strictly speaking, symmetries of any nonlinear K3 sigma model, but this is where our overarching group Z2 to the 4 times A8 sits, really. So that's there. So, in a nutshell again, and I hope that Catherine convinced you that all this is perfectly reasonable, as I wanted to motivate very briefly why we restricted our analysis to geometric symmetries. Bearing in mind that in the second part of the talk, I will concentrate on superconformal field theories which are Z2 orbifold of toroidal theories. And the reason why I chose this class will become quite obvious when I've started talking about the class of K3 surfaces that we are looking at. Now, in these theories, you have two free Dirac fermions, chi plus and minus here, and we to justify a little bit the geometry here, we argued on the Ramon ground states of these theories, which have 24 ground states, which organize themselves into 4 which are twisted and charged, 4 and twisted and charged, and then 16 twisted and charged ground states TA here. So I'll say more about this later on, but if we would spectral flow from the Ramon sector to the Neveu-Schwarz sector, then we would land on a vertex algebra here in the Neveu-Schwarz sector that contains in particular the chiral algebra of Lurch, Waffer, and Warner. This has been established a long time ago. And this chiral algebra is, or can be viewed as the leading order of a graded vertex algebra. Right? Now, it's also known that you can identify this chiral algebra with the cohomology of K3, of the K3 surface that you are looking at. So all this is, has been known for a long time. And as Catherine motivated here, is that if we look at symmetries of these conformal field theory that descend on the chiral de Rham complex, then of course you have a link between the fact that, you know, a component of this complex is going to be helping you identify the chiral algebra here with the cohomology of the surface here. So in order to have this property for these symmetries, that they could descend to this one, the list of things that Catherine talked about, at least she talked about fixing the U1 currents. And incidentally, you also need this already to spectral flow to the right sector in order to see these structures. We choose a preferred n equals to 2 subalgebra into n equals 4. We also want to look at symmetries that fix the n equals 4 superconformal algebra pointwise. And this is also a crucial ingredient in the work of Gabadil and company here. And then, in order to be able to perform a large volume limit at the right stage, we need to know what we need to fix a geometric interpretation of that conformal field theory. So all this means that you restrict yourself to the geometric symmetries.
I have a naive question about that. Does that allow like B field deformations?
You can have, you could put B fields in the story. I mean, we didn't need that to do our calculation.
When you say geometric, you mean?
Geometric means that you can fix a B field which is non-zero.
Geometric interpretation means you fix a B field in a complex structure.
Right. So again, quite briefly, because it's, I suppose, stuff that people know, if we have a K3 surface, then we have associated to it a very beautiful lattice of rank 22 here, and this signature here, which is usually called the K3 lattice. And it can be put into the form of 2 copies of the E8 lattice with a global reverse of signature. So that's the meaning of this -1 here. And then 3 copies of the hyperbolic lattice here. Now, associated to this rank 22 lattice H2, we have one which is slightly bigger, which has now rank 24, because we add a copy, essentially, H0 plus H4, a copy of this lattice U11. And this lattice is also even and self-dual. And the fact that we have this property here, even self-dual lattice, is again extremely crucial in order for all the calculations we do on the lattices to be consistent and well-defined. A lot of what we have done relies on deep results by Nikulin in particular, not only, and he has a lot of very powerful results here relating to even self-dual lattice that we have used. Now, to fix notations and jargon here, so we are looking at symplectic automorphisms of a K3 surface, by which we mean this, that we have a map from the surface to the surface itself, biholomorphic, so meaning that F and F-1 are bijections, finite order. And on top of this, if we now look at the induced map on the homology, the full homology H star of XR, then this induced map is going to must preserve the complex structure. So that's symplectic. Now, Mukai's classification has to do with finite groups of symplectic automorphisms. So this is linked to the fact that we are looking at holomorphic symplectic automorphisms. That's what's explained here. So let me say what an holomorphic symplectic automorphism is. Well, on top of preserving the complex structure, the induced map also preserves a dual Kähler class on K3. So the theorem is that if we look at non-trivial group of symplectic automorphisms of a K3 surface, then we are guaranteed that Gx is finite if and only if X preserves a dual Kähler class here. So instead of saying finite groups of symplectic automorphisms I can say holomorphic symplectic automorphisms. Right, that's what I say here. And here we go, they are determined by these two complex structure and dual Kähler form. So, just in case somebody hasn't seen this paper, this is Mukai's table of the 11 groups, and the claim is that all the finite groups, so the holomorphic symplectic automorphism groups of K3 surfaces, must be a subgroup of one of these 11 ones here. And as Katrin has already shown you, the largest one is size 960. Right, so it's not terribly big compared to the size of M24. Right? And what we are looking for is actually a symmetry which is going to overarch all these symmetry groups. Now, in order to do so, we really concentrate again on this lattice of rank 24, which is even and self-dual, because any discussion that one might have on symplectic automorphism of the K3 surface can be translated into statements about lattice automorphisms of the full integral homology lattice of K3. So this is a theorem, and we are going to use and abuse it really here. And the second thing is that although we know the structure of H star xz, that I'll show you before, it was 4 copies of U and 2 copies of the 8 lattice, it turns out that in a special class of K3 surface that are called Kummer surface, and I'll explain what they are in a minute, then we have a very neat and a useful way for our purpose to reconstruct both this one and the full one. Actually, we can reconstruct the full one just by using knowledge of a sublattice which has very specific properties. Now, this is a little bit technical, and I have no time to go into the details here, but because this one is even and self-dual, and if you know a sublattice which is called primitive, so obeys certain conditions, then you can reconstruct the full lattice from the knowledge of this sublattice by gluing techniques. And this is a whole set of techniques that have been developed by Nikulin. Right? And we use these in this case, so this is very, very classical, very well known to the experts, I would say. Which I learned them from Katrin. But so, why are Kummer surfaces so nice for us? Well, the way they are constructed is by first looking at a torus. So here we go. We have 2 copies of the complex space, and we model by a lattice that I'm going to call L. And then we take a Z2 orbifold of this torus. So this lattice is 4-dimensional, and we have a point identification through this procedure, this double procedure. So this is obviously the torus, the periodicity, and this one is implementing the orbifolding. And we look at the fixed point of this set of relations, and it's not too difficult to find that actually the fixed point can be parametrized by a 4-plet of numbers here, which are normalized here to be 0 or 1. And these 16 points belong to the space F24. Now, so far, this is not a smooth K3 surface, so because of the singular points. So you have to resolve the singularities, and this is standard procedure as well. And once we go through the procedure of resolving the singularities and obtain a smooth K3 surface, we introduce some two cycles in the game, and there are 16 of them, corresponding to the 16 singularities here. And these I chose to write as EA, EB, and you see that the vector A here is one element of F24. And here we go, the lattice that one uses in our construction to reproduce or to rebuild H star XZ eventually is a lattice which is 16-dimensional, so rank 16, which is built out of these two cycles. And the fact that I have another 5 generators here in the lattice, or objects, vectors in the lattice here, is to ensure that this lattice has the right properties to be glued to its complement in order to reproduce H star. So this is basically prescribed by the Nikulin gluing techniques, right? So again here, there is a lot going on, but I'll skip over the details. Right. So what kind of symmetry, so geometric symmetries do we have on a Kummer surface? And again, this is well documented. The structure is Gx, so X will always refer to my Kummer surface in this talk. And it is a semi-direct product of 2 finite groups. One that I've put in pink here is also going to be recurrent through the talk because it's actually generic to all Kummer surfaces. The little t here means translations, all right? And I'll explain this in a minute. And then the other group, and it's normal in GT. Now, G capital T has to do with non-translational, non-translational symmetries of the surface here. And they've been classified, at least the ones that are induced, these ones are induced by the symmetries of the underlying torus, and these symmetries have been classified in 88 by Fujiki. So we have a whole list at our disposal of what to expect for G prime T, of course, and then GT. And the maximal such G capital T here happen to be these 3 groups, Z2 cross Z2, A4, or S3. And these, of course, this part of the symmetry is very much dependent on the lattice that we've used in order to construct our torus. So this lattice here is a square lattice. There's this symmetry. This is a tetrahedral lattice, and this one is a triangular lattice. So any group Gx is a subgroup of one of these 3 here. Right? Now it, as a whole, sits into this group, but I will say a little bit more about, so this is still a discrete group. This is the alternating group of 6 elements. So the permutation of 6 elements which are even. But it sits in a slightly bigger group, well, not slightly, in a bigger group, which is Z2 to the 4 semi-direct product with SO3. Right? And this will become relevant later on. Now, coming back to the first part here, the translational part here. So if we look again at the structure of the singular points, written in this normalization, so the 1/2 allows me to have these points A to be 0s and 1s, all right? And if we shift by half lattice vectors, then we actually travel from a particular point of F24 to another one of F24, and this generates translation in the 4 directions of the space. So you see that at this stage, to do this calculation, I don't have to tell you anything about the actual nature of the lattice that I'm using. I just say that there are some lattice vectors there. So this part is generic to all Kummer surfaces. So you always expect this to happen. And this will be echoed in the CFT, and I'll tell you already how it will be echoed. It will be echoed by the presence of 16 twisted ground states that I've already alluded to before. So these twisted ground states, you can see, are related to the singular points of this construction here of the Kummer surface. Right. So yes, so as I said, we permute the A's by this kind of symmetry here. Right. So another important point about the Kummer lattice that I've just described is the following. that we expect the geometric symmetries to act on the whole lattice, the cohomology lattice here. We would like to pin down a little bit better the structure of this action on the lattice. It turns out that according to this, which is a theorem that can be traced back to Nicolin as well, the Kummer lattice, if you know the action of Gx on the Kummer lattice, then it's enough to determine its action over the whole lattice. So having a good grasp on the Kummer lattice is a must in this problem. So let's go through the statements here. So if we have a symmetry of Gx, and then its action on the lattice that is well, an action which is induced from there on the lattice here, then we know, what did I want to say here? Okay, so it's a set of statements here that actually paraphrase what I said before. Let's just concentrate on this one, is that the geometric symmetries here are going to fix a particular vector on the Kummer lattice. So everything else will be transformed, but if we take the sum over all the F24 points here, 16 of them, then because the group essentially acts with translation, because we take the sum, then obviously it stays invariant. So this quantity here will reappear as well later on in the context of the CFT. Right. So this is a statement here that I've explained before, is that Gx is this semi-direct product here. This sits into the group of linear map on F24, and it turns out that this, which is defined by this semi-direct product, Z24 times the group, linear group on F2 here, this group here is isomorphic to A8, which is quite a non-trivial little result there, but the fact that it's A8 is important for us.
The previous slide you had A6, so that's pretty cool.
Sorry?
The previous slide you had A6.
Yeah, E6.
So A6.
A6.
All the groups sit at
Yes.
A6, but A6 sits at A8.
Oh, sorry. Wait, that was
So far, we've talked about classical geometry of K3 surfaces. And now, although Mukai already knows that M23 plays a role there, and hence M24 could play a role, we were quite intrigued by how we could concretely see the action of M24. And this is why we started to work with a Niemeyer lattice in conjunction with all these ideas from geometry, and see if we could represent these symmetries of Gx as a permutation of S24, but which were inside M24. So you know that M24 is a subgroup of the permutation of 24 elements, and a very specific one. So that's how we did it. So Jeff has already introduced the Niemeyer lattice that we are going to use here, which is the one which is based on the root lattice of A1 and 24 copies of A1. The reason why we pick this one and not any of the other 22 that are at our disposal, right, because will be explained in a minute, the next transparency. And as Jeff explained, you start with the root lattice of A1 to the 24, but this is not self-dual, and therefore you have to use gluing techniques again here. And the way you glue is that you use vectors. I mean, it's expressed here in a particular form, but basically here the representative of the coset class is in this. R star over R, so this is the dual lattice to R here. These are bunches of zeros and ones, and 24 multiplets of them. And these vectors made of zeros and one can't be arbitrary. They have to belong to the so-called Golay code, the extended Golay code. And this is a very, very brief summary of what this Golay code is. So it sits inside a 24-dimensional space here, F2 to the 24. So we can think of the elements as a bunch of 24 entries here with zeros and one. In such a way, and our code words, the weight of a code word, so this is called a code word, the weight is the number of non-zero entries, and it's characterized by the fact that there are no code words of weight 4, and they can be of weight 8, 16, and 24, and 12, sorry. And this is the decomposition of how many words there are in these weights. And the dimension of the code is 12. So this is an example of an octad, because it's weight 8. And you can write an octad in two different notations. Basically, this one tells you which entry in this vector you have a 1. So 3, and then 5, and then 6. Right. So that's...
So weight means just the number of ones?
Yes.
Weight is just the number of ones?
Yes.
And dimension means the number of weights?
The dimension of the code is basically the power of 2 that you have here. And so this is the total number of words that you can construct that are constrained by the Golay code.
G24 is a subspace of F2 to the 24, and its dimension is 12. As a vector
Yeah.
space.
And what is new bar up there?
Well, this is, so in each, so if you take R star over R, the classes are 0, 1. Yes? Now you have 24 copies of this. So you can think of this as vectors with 24 entries, zeros and ones. Yes? But you only keep such, so this would be one of them if you want. So you would use, so in the Niemeyer lattice, you could use this object here. But if you would put 3 ones and a bunch of zeros there, it wouldn't be a word of the Golay code, so you couldn't keep it in constructing your Niemeyer lattice, right? So it gives you a selection rule of a very specific kind. And it turns out, as you know, that the M24 is the group, well, yes, it's the automorphism group of the Niemeyer lattice, essentially. Right. Okay, so it's a bit detailed, this, and nitty-gritty, but when you actually do the calculations that we did, you need to go into very specifics, yes, and this was helpful. Right. So what we found, and this was our first beautiful and exciting result here, is that the Kummer lattice that we really wanted to understand can be shown to be isometric with a sublattice of the Niemeyer lattice in question, with exactly the right properties. Okay, I should say the Niemeyer lattice has a signature which is 24-0, so all pluses, right? Now, if you flip the sign of everything, you get 0, 24, which is now why I can write an isomorphism, an isometry here, in fact, between what I call pi tilde that would sit into the Niemeyer lattice, but then if you flip the sign there of all the component, it has exactly the same signature of the Kummer lattice. Kummer lattice is 0, 16, right? So,
can you remind me what the primitive condition is?
Primitive. Well, essentially, it means that the lattice is sitting at the intersection of
Orthogonal to orthogonal brings back to lattice. That's what it means. If I take the orthogonal of pi twiddle, and then the orthogonal of that, I come back to the pi twiddle and get any addition. We don't get finer. It's not the definition, but that's kind of the effect that it has. You don't miss out any vectors.
Yes, so another way to say it is with the coefficients being in Q, if the lattice admits combinations which are rational, not just integer. Yeah. Right. This will be important in the dictionary between the lattice of homology in the geometric side for K3 and the lattice, the Niemeyer lattice here, because what we want to do is exactly that. We want to construct a linear bijection between H star xz and the Niemeyer lattice with signature reversed here. So whatever action of the group, symmetry group here is, we would like to encode into a language that is obviously related to M24. And as I said, the way we did it is by expressing all these symmetries in terms of permutation of M24. So permutation on 24 elements, but that sit in M24 and not in S24. And of course, you have to make a lot of checks when you do these calculations, but that can be done. So the fact that we have an isometry for the Kummer lattice, now the Kummer lattice is a sublattice here of H star xz, and at that level we have an isometry. Right? So the idea was to try to build up a linear map, linear bijection, starting, which would restrict to this isometry on the Kummer lattice. And we did a little bit more than an isometry on the Kummer lattice, as you will see. We could enlarge our lattice a little bit here and find an isometry which is a little bit on a bigger lattice here. So as I said before, having this isometry is important because we know that if we have control of the action of the group on the Kummer lattice, then it's enough to determine the action everywhere. So when we transport by the linear bijection, we will have the same phenomenon here, that we know the action on the pi tilde -1 lattice, and then we can reconstruct the action over the whole Niemeyer lattice. Now, as I said before, this combination here on the geometric side is invariant under these geometric symmetries. And this can be expressed by this fancy language here, is that actually in the Kummer lattice, this is the only object which is invariant under Gx. This notation means I take all the parts of the lattice that are invariant under the action of Gx. That's what this means. And then the intersection with pi is just this element there. Yeah?
So the Kummer lattice is defined particularly for this T4 mod Z2 portion, right?
Yes.
But if I did say T4 mod Z3, there would be some analog of the Kummer lattice?
Would it be?
It would be the Kummer lattice.
It wouldn't be a Kummer lattice, would
It
it?
wouldn't be a Kummer lattice, but there would be some lattice that's defined. And do you know if that lattice would have a primitive embedding in some other Niemeyer lattice?
Well, I don't know that.
I mean, I guess I'm wondering if there's some lattice that rises in some kind of orbifold degenerations of K3, where this is one of many examples, and the lattice that you get always has some embedding in a Niemeyer lattice, but they're different Niemeyer lattices depending on which orbifold.
B8 to B8.
What? Yeah.
Or that your report should be B2 to B8.
Maybe, yeah.
If you put down
So-
you will get issue 3 to B8.
Right.
And
Right.
So the lattice is, the analog of the Kummer lattice is known for all these orbifolds. I just don't know which Niemeyer lattice. I'm pretty sure we should have, each orbifold we should find a Niemeyer lattice for the Kummer analog. And that's
more than one.
So it could be that all the other.
For other, in this case no, but in other cases it does could be more than one.
Yes. Could be able to find more than one Niemeyer lattice.
Yeah. Yes, in a way, it would make use of all the other Niemeyer lattice, maybe. because this is definitely we needed the A124 for this construction to work.
But the beauty of the Kummer construction is that it works for all tori. If you start using
Right.
other
Then
orbifolds,
yes.
then kind of your modular space becomes much
Exactly,
smaller.
yeah. And the symmetry group is small.
Yeah.
But,
Mm.
it's not, that's kind of what happens on illusions.
Right. So as I said, we want very much to keep the Kummer lattice. On the other hand, we were aware of the work of Kondo, who gave a lattice proof of Mukai's result, actually, where he introduced the technique of looking at the part of the lattice which is invariant under the symmetry, so L upper GX in my notation here, and using its complement into H star in order to prove the fact that the action on that part of the lattice on this geometric side would actually induce an action on the other part here that you could reconstruct for the whole group here. So it's a beautiful argument there. But this Kondo lattice is actually a sub-lattice of what I've highlighted here in red, which is what we constructed. So we constructed a lattice which definitely contains what Kondo would have used in this case. This means the complement of the part which is invariant under GX. And even Kondo, in his paper, in a slightly mysterious way, had to append to this lattice the span, so a one-dimensional lattice here, the span of a root, right? And we understand now what this root that it seems to be quite ad hoc in this paper here, is actually linked to the direction which sits into the hyperbolic directions of the lattice, the U. So epsilon naught and epsilon are the generators of H0 and H4, the components of the lattice that I showed you in the first transparency. And this has norm -2, so this is actually the identification from the geometrical perspective of what Kondo had in his paper already. But what Kondo didn't add in his construction is actually this vector here, which we need here because we need the full Kummer lattice to be represented. And because this E element was invariant, it was left out by Kondo. I mean, of course, Kondo was doing a different construction. He was not looking at Kummer surfaces in particular. So here we go. So we have a new lattice MGX, and this lattice MGX, of course, depends on the symmetry group that you are looking at, right? It has this structure, and its rank is at least 17. That's because you add this direction and this direction here. You could have nothing else. I mean, the full Kummer lattice is rank 16, and then you add this direction here, that's 17, and then everything else, of course, depends on the group that you are looking at. And its maximum value is 20 there. Now, after quite a few creative ideas here, we managed to construct an isometry here between these lattices MGX and one which is embedded in the Niemeyer lattice here, but then also construct a linear bijection here that extends to the full 24 rank lattice here and this one there. What's important is that there is, in this construction of the isometry, you have no choice. So everything is fixed. Now, in order to construct the linear bijection there are a few choices that you have to make. But the important thing is that for the Kummer lattice part, everything is beautifully fixed. And of course, this bijection depends on the group you are looking at. So you expect that if you take different models, different lattices, then you get a different bijection. It turns out that if you take the tetrahedral lattice and the square lattice, for example, and you go through the motion and the mechanics of constructing the bijection, then you see that you can you can use the same bijection for the two cases. Now, this symmetry group here was the generic part times A4, and this one is Z2 cos Z2. And now we say that this is a crucial point here, is that because you can realize on the Niemeyer lattice the two models by using the same bijection, it makes sense to combine on the Niemeyer lattice here the two symmetries. So this is really the jump, if you want, between looking at models, nonlinear sigma models on K3 to something that is transcending them here, right? So this is the first step into the surfing argument here, is that somehow you have a device here, which is the Niemeyer lattice, that allows you to collect the symmetries, at least of these two models at the moment. And then you look at the other ones. So you remember that there was a third maximal group, GX there, which is the triangular one. And what you find by doing the calculations very precisely is that in the same way as there was this unique bijection that links these two models from the previous transparency, you also have a unique bijection, different from this one, that links these two models, and another one that links these two. So already, without ignoring the white line for the moment here, so somehow you could combine the symmetries of these two already, and this is this group. So you see that you go beyond any group in the Mukai classification here. But this is still in M23. So you combine these two here, and you get the same group, it turns out. And if you combine these two, you get the dihedral group here. So now this is not enough. I mean, the fact that you have M23 and not M24 can be argued from the details of the calculation here. But what we see is that now if we find a way to move from one maximal group to another maximal group through a path of theories, which I call generic Kummer surface here, where you are guaranteed that at minimum you have the Z2 to the 4 symmetry, because it's generic. So we can show that we can actually travel between these two maximal groups there, and connect everything together. So that's the surfing idea here. Then our construction and our idea is that you can now make sense of combining the symmetries that you have obtained in each of the pairs here. And that's at that stage that we reach the group that Catherine showed you before. So Z2 to the 4 times A8 is actually obtained by combining all the symmetries that you can collect in that class of theories from the symmetries of these theories.
And could you show the previous slide?
Yes?
So you take symmetries on the left-hand side and you use this isometry to map them to the right.
Yes, yes.
But what happens if you take an automorphism of the Niemeyer lattice and can you use the inverse of this map to get some action on the model on the left-hand side? Or I don't know. I guess I'm just kind of confused about how this mapping. You described it, but I just don't quite understand it. But you can't take things on the right-hand side and map them back.
Yes, you can.
But what do? If you take some symmetry of the Niemeyer lattice, it's not in one of your symmetries actually on the left, and you map it back, what does it do?
Well, of course, we restrict to symmetries that act trivially outside of the red lattice. Those would be the red lattice, the MG on both sides. Those are positive definite. So on that level, it makes sense to do negative lattice.
Okay.
But it's actually crucial that, I mean, we're making many choices and we're playing this game of extending the isometry to something that maps it to like 24 lattices. And it's kind of unclear how to interpret this on the part which has the wrong signature. But pulling the symmetries from left to right is completely independent of all the choices that we're making there. So you don't even to translate the symmetries from left to right, you don't even need to make that choice of the math theta. All you need to know is how they act on the Kummer lattice. So that's actually crucial. I mean, we like this idea of surfing and deforming the surfaces and then kind of keeping the same math that compares the lattices, but you don't need that in order to induce the action of the symmetry groups on our device and on the right-hand side. There are no choices involved there, and that's actually crucial. Because otherwise, I mean,
It'd be very arbitrary.
Exactly. Otherwise, it would be completely arbitrary. But the whole point is, and Anne emphasized that, is that the Kummer lattice contains all the information you need in order to say how the symmetries act on the rest of the lattice. These are these new techniques.
You're calling this MGX, you're calling it the Kondo lattice?
That's
No.
bigger than the Kummer.
No.
It's a little bigger.
Kondo is this part here.
Is
Here.
there a relationship between M and the card lattice?
Between what?
The lattice MGX and the card lattice of the K3 surfaces that you're getting?
I think the Carl lattice is contained.
Is what?
I think the Carl lattice is contained in the
Picard.
Ah,
But let me think about it and tell you afterwards. Yes, it's not hard, but I can try it out. I
right.
think the Picard lattice is automatically contained in there because the transcendental lattice is fixed by our symmetries by definition, and this guy is kind of the orthogonal complement of the transcendental lattice, but even a little bit bigger, so it contains the Picard lattice.
Okay. Right. So this is the idea of the surfing. Well, you can buy it or not buy it, of course. So what I'm going to do in the remainder of the talk, which is, I don't think I have too much time, is to argue that from the CFT point of view, you have support for this, for this construction that we had on the geometric side. So to summarize, the geometric group GX that has this shape that we saw before, I did say that GT is actually sitting into SO3, right? There's A6 as well, but I mean, I'm emphasizing the fact that it's a subgroup of SO3 here. And if you look at this geometric symmetric group, as we said, they generate an action which is an action that is now sitting in M24, but not in M23. So crucially, the Kummer surface and the Kummer lattice, which corresponds to the 16 fixed point here, was important. And then in the CFT point of view, where we look at the Z2 orbifolds, the 16 twist fields are basically connected directly to these 16 fixed points. So you expect the properties under the groups to be the same. So the strategy that we used there in order to calculate something that was relevant to our ideas was to take the elliptic genus and concentrate on an explicit construction of the 45 states that we see in the in the Matthew-Moonshine phenomenon there. So we looked at these Z2 orbifolds and computed these states. And then, after having an explicit description of these states, we looked at how these GX groups were acting on the states. So very, very briefly, the content of the holomorphic sector is in terms of two complex currents and their conjugates, so J plus and minus, 1 and 2, and then the superpartners, the Dirac fermions and their conjugate, which I call chi, and then the n equals 4 content in terms of these fields is schematically given by the usual thing here, so the bilinears in the currents here for the energy momentum tensor, and then the supercharges as a combination of fermions and these U1 currents, and then again, the Katz-Moody ones there. Right, so we don't need the details of this table, but just to say that, I mean, the ground states in the untwisted sector are 4 charged one and 4 uncharged one. And then we also have in the twisted sector of the theory the 16 ones, just to fix notations. And if we would compute the partition function for this type of models, this class of models, that's what we would see. So each model will have a different description of this, this part here of the partition function, because it depends on a particular lattice that you look at. But the generic part is contained into everything which is written in black on the board here. So that's the elliptic genus, we know. And now we count the states. So it's a straightforward exercise, starting from the expression on the previous page, to identify these 45 plus 45 states in the elliptic genus. And here they are here. So from the untwisted sector, which is the first part of the expression, and as far as generic states are concerned, we looked at states which have conformal weight 5/4 on the holomorphic side and charge +1. That's a choice we made. It's good enough. And on the anti-holomorphic side, we stay on the ground state, so Q bar equals 1/4, and the charge here is anything we like. And here's the content. So from the untwisted sector, we have states which happen to be massless. By inspection, we discover that. Is that we act on one of the charge vacua that I wrote in the previous table, and we have a combination of 3 fermions, and then these are the modes of the U1 of the J's currents, the U1 currents that I had on the previous of the bosonic currents that I had on the previous page. We have another bunch of states which are bilinear in the fermions here, and then some here which have 4 fermions in their construction here. Now the indices little k and little l vary from 1 to 2, and capital K varies from 1 to 4 because we have a T4, so we have 4 directions there. Now we can split these contributions, so we have 4 contributions here, into a massless one and 3 massive. And here again, same thing, there is 1 massless combination and 3 massive ones. So from the untwisted sector, as far as counting the elliptic genus, we have to concentrate on the massive states. So we see that we have a contribution of 6 here. Now we go on the twisted sector, and we do exactly the same kind of little analysis, and all the states of interest are of this shape. So they act, these are the twist fields, 16 of them, and then we have a fermion and a boson acting here. And there are 16 times 4 times 2, so 128 states in this collection here. And again, we can split them into masses and massive contributions. They are all fermionic. And we have 96 fermions. So this is a particular class of model where 45 or 90, let's say, is obtained by the subtraction of 6 from 96. So 90 comes as 96 minus 6. Now, in other models, as was pointed out before in this conference, you could get to 90 with a different counting. So it could be 102 minus whatever gives you 90, for example. So this is specific to this class of models. And of course, one question is, which 6 states in these massive ones are the ones that I should cancel with these ones? So it turns out that that is fixed as well. There is a unique way to do it. So here we go. This is an explicit representation of the states from the previous transparency coming from the twisted sector. So the massless states are combinations of the fermions and the bosons here. Now what I didn't say or repeat is that the SO3 component So GT, the group, the geometric group is a subgroup of SO3, so we can think of SO3 as acting on, well, it's actually SU2 acting on Chi1, Chi2, there's a doublet there, but because the action of -1 is trivial in the states that we are looking at, then it's actually SO3 that comes into play here. So we can decompose the contribution here into representations of SO3. So these are two singlets of SO3, and the orthogonal states to these ones, which appear here, make two triplets of SO3. Right? So we have 3 times 16 twist fields here, plus 3 times 16. Right? So this is 96. So how do I decouple the 6 states that are going to cancel the bosons from the untwisted part of the sector is explained here. But I suppose I'm over. Yeah.
How much longer?
Not too long. I just usually, yes, 5 minutes probably. So here, out of the space which is made of the 16, generated by the 16 twist fields here, I can decouple one direction. Now, remember that there was a very special vector in the Kummer lattice, which was E, which was linked to the sum of all the 2 cycles here. So here we have the equivalent statement here is the right normalization here, where we take a sum over all the twist fields. I didn't say it here, but the 16 twist fields are involved here. And this combination here is now, we construct the orthogonal space to this direction here that we call calligraphic A here, right? So we have a 15-dimensional space orthogonal to this direction there. And this is how we obtain a vector space here, which decomposes into a 3 of SO3, and this 15-dimensional vector space there on which the group G acts. Now, this was the CFT point of view, so we understand how the group acts on the states that we have extracted from the partition function and the elliptic genus of the Z2 orbifold. And of course, we wanted to relate this, if possible, with data from group theory, because it turns out that there is an explicit construction of a 45-dimensional representation of M24 in the literature by Margolin back in '93. And luckily for us, the representation that he provides is particularly suited in order to make comparison with what we obtain from the CFT point of view. Now, it's very schematic here, and the paper is beautiful, but involved for non-experts in group theory and representation theory, like I certainly was not before I started looking at Margolin's paper here. But the essence of his construction, so now we are talking about constructing a vector space that accommodates a representation of the full M24, right? And it's built as a tensor product here of a complex three space here times a base space which has 15 components in it. So another way to write it is 15 copies, because A to O means 15 labels, 15 copies of this C3 space there. Now, Margolin explains how to act on this space with an M24 action, but very helpful for us is that he looked separately at the action of the Z24, the action of the A8, and then he goes on and has an extra generator that will allow us to go from Z2 to the 4 times A8, which is a maximal subgroup in M24, to the full M24. Now, we don't use this information in our approach here, but we very much liked to understand this in the context of Margolin paper and see how this translated into our CFT understanding of the states. Right? Bearing in mind that Z2 to the 4 times A8 is not a symmetry of our conformal field theory. Right? And actually, the punchline of this construction, and I'm kind of aware of the time, which is just escaping too quickly here, but the punchline is that actually, in order for the group Z2 to the 4 times A8 to act on this vector space in Margolin's construction, you have to take full advantage of the fact that this construction of the space, the action of this subgroup here on the space doesn't factorize into something acting on 3 and something acting on 15. Now, in the CFT part, remember, we had the SO3 action on the 3, and we had the full group acting on the 15. So here, what happens is that when you act with A8, for example, you permute the different labels here, A, B, and O, but at the same time, something happens to what we could call the fibers nu here, and they are twisted. So there's something happening to the fibers as well under the action of A8, which is not something which happens to be what it is. Now, in any conformal field theory, you don't have at your disposal any symmetry group that would allow for this twist. This is called the twist, this action on the fiber induced by the action on the basis. And therefore, let me finish by stating the result precisely here of what we discovered by comparing the two, is that on the one hand, we have the vector space of states constructed from the CFT, which is a tensor product of 3 and this 15-dimensional space A, and on the other hand, we have the Margolin representation, which is 45, that I tried to show you very sketchily before. Now, if we consider a geometric symmetry group of our Z2 or before conformal field theory, right, and its action on the vector space V445 CSD, then what we could show is that this vector space of space here is equivalent, well, this space here is equivalent to the Margolin representation as long as you restrict to these groups G. Okay? So the group G acts on our CFT space as it acts on the Margolin representation. So that's quite nice.
You mean there's no twist in those?
There is no twist. So as long as you have the geometric symmetry group, there's no twist involved. And this precisely is good you say that, because as soon as you go to Z2 to the 4 cross A8, which is our overarching group, you get a twist. As I told you, Margolin shows you that, I mean, this action produces a twist. So this reinforces the statement that there is a jump between what you can do with the geometric symmetry groups and what you could do with this combined symmetry, overarching symmetry. So there's a kind of obstruction. In the same way as for the construction from the Kummer surfaces, we know that there is a maximum group that you can have for the geometric symmetry, and it's not terribly big. Okay? You can't go there to Z2 to the 4 times A8, for example. The way we argued about that is through the overarching procedure, but it's not a symmetry of a nonlinear sigma model. Yeah? So in the same way, if we had these geometric arguments for that, now we see that in the context of the representation theory, if we were dreaming of a group of a nonlinear sigma model of that class that would be too big, then we would encounter the problem of the twist. Right? So it's another way, that's why I say it's evidence for what we saw in the geometric setting, is that even from the representation point of view, we know that we have a limit beyond which we can't go if we restrict to, strictly speaking, symmetries of the conformal field theory. So it doesn't solve any problems, but it just emphasizes that you can think of this. So what you can now think of is that you could use this space, V45 CFT, as again a medium where you could collect symmetries from different conformal field theory, and you could try to play the surfing game, but in the conformal field theory context. So that's the idea behind this kind of construction. So it would be very nice, for example, to confirm similar ideas for higher contribution in the massive spectrum, for example, and see how the states there organize themselves in terms of representation of M24, and how much we see and how much we can't reach. Right. So I think I'll leave it to here.